So, quick poll ahead of time. How many people here have been programming in Go already? Most people? Excellent. All right. So we're going to go a little bit deep today. Let's see how this goes. My name is Jon Bodner. Hi, welcome. I'm a senior staff engineer here at Morning Consult, and today I'm talking about reflection in Go. So we're going to cover what is reflection, the kind of problems that can be solved with reflection, the concepts behind reflection in Go, which are types and kinds and values. How to use reflection to create variables and functions and structs. Uses of reflection in existing libraries, and I'll build a couple tools using reflection to see the kinds of things that you can make. So one of the things that people who use Go like about it is that it's a typed language, right? So most of the time, declaring variables and types and functions in Go, it's all pretty straightforward. You need a type, you just define the type, right? And you need a variable, you just define the variable. And when you need a function, you just define the function. And in general, types in Go are the data structures that you knew you needed when the program was being written. And this is really handy because when you have types as such a core part of the language, the compiler helps you make sure that your code is correct. But sometimes relying on compilation time information is a limitation. You might need to work with variables at runtime using information that didn't exist when the program was being written. And maybe you're trying to map data from a file or a network request into a variable, or you want to build a tool that works across different types. So for those situations, you need to use reflection. So reflection gives you the ability to examine types at runtime, and also allows you to examine and modify and create variables and functions and structs at runtime. So when do you need this kind of functionality? So if you look at the Go standard library, you get an idea of where reflection is needed. Most of the uses of reflection in the standard library, they fall into 5 general categories, really. First is reading and writing from the database. The database SQL package uses reflection to send records to the database, and then to pull data back out again. Second use of reflection in Go is the templating libraries. So reflection is used to process the values that are passed into the templates. The third place that Go standard library uses reflection is the func package. So all those calls you make to func.println, that's actually using reflection behind the scenes. The last main usage of reflection in Go is from marshaling and unmarshaling data to JSON and XML and the other data formats defined in various encoding packages. So struct tags are actually accessed via reflection, and the fields in the struct get read and written using reflection as well. And there is this 5th use of reflection in Go in the standard library. It's for testing. So in the reflect package, there's this function called deep equal. And it's in the reflect package because it takes advantage of reflection to work. Deep equal checks to see if 2 data types are deeply equal to each other. And this is a more thorough comparison than you get with the double equals. And it also lets you compare things that you can't normally compare with the double equals, like a slice or a map. And most of the time, you don't really need it. The Go standard library primarily uses a check during tests to make sure the values that came back actually matched up. But it's in your program, you want to make sure the 2 maps have the same keys and the same values. You want to compare 2 slices. Deep equal is available for you to try to use. So now that we know what reflection actually is and why you might need it, you still need to understand how it all works. And reflection in Go is built on 3 core concepts. There's types, and there's kinds, and there's values. So the reflect package in the standard library is the home for the types and for the functions that implement reflection in Go. Create more chairs. All right, so first, let's look at types. We use the word type an awful lot. Bear with me. Get up with it. A type in reflection is exactly what it sounds like. It defines the properties of the variable and what it can hold and what you can do with it. So with reflection, you're able to query the type to find out about those properties in your code. You get the reflection representation of the type of a variable by using the type of function in the reflect package. And so the reflect type of function returns a value of type reflect.type, which represents the type of the variable that's passed into the type of function. And the reflect.type type defines all these methods with all sort of information about a variable's type. And we can't cover all the methods, there's like dozens. But here are a few. So first method we'll look at in reflect.type is called name. And this returns, not surprisingly, the name of the type. So looking at our example here, we start with the variable x, which is type int, and then we pass it to reflect type of to get back a reflect.type instance. And for primitive types like int, the name we call name on reflect.type, you get back the name of the type, so name returns int. And if you define a struct, the name you give the struct is returned. So we define a struct called foo, and you pass a variable type f of foo named f to reflect.type. You print out the name returned from the reflect.type instance, you get back foo. So some types, actually, like slices and pointers, they don't have names. It's a little bit weird. The name method returns back an empty string. So if you pass a pointer to x into reflect type of, and you call some println, and you print it out, you actually get back just an empty string. Next method, this method is actually incredibly useful, is kind. So this returns a value of type reflect.kind. And reflect.kind is a constant that says what the type is made out of, what the storage behind it is. A slice, a map, a pointer, a struct, an interface, a string, array, a function, an int, or other primitive types. And the difference between the kind and the type can be tricky to understand, but think of it this way. If you define a struct named foo, the kind is struct, the type is foo. And the kind is really, really important. It's one thing to be aware of when using reflection. Everything in the reflect package assumes that you know what you're doing. So some of the methods defined in reflect.type only make sense for certain types and certain kinds. And for example, there's a method on reflect type called numin. And numin, if your reflect.type represents a function, returns the number of input parameters to your function. If your type instance is not a function, it panics. And in general, if you call a method that does not make sense for the kind of your type, it's just going to panic. So always remember to use the kind for the reflect.type to check to see if what's been passed in actually does work correctly, so you can use the correct methods on reflect.type. And that way you know which ones work and which ones are going to panic. Another important method on reflect.type is ln. So some types in Go can have references to other types, and ln is how you get that reference to that contained type. So for example, you should reflect.type on a pointer to an int variable. So that gives us a reflect.type instance of pointer to int variable. And that gives us a reflect.type kind, has the type comes back as a blank name, and the kind comes back as ptr pointer. And if you look at the reflect.type returned from the lm method on a pointer type, you get back a name of int and a kind of int. So when you have a pointer, lm tells you what the pointer points to. And lm also works with slices and maps and channels and slices and arrays. Reflect.type also has support for reflecting on structs. So if your reflect.type's variable is kind of a struct, you can use the numField method to get the number of fields in the struct. And you get the fields in the struct by index using the field method, which returns back each field structure contained in a reflect.structField struct. And the reflect struct field gives you the name, the order, the type, and the struct tags on the field. So this is how if you put struct tags in the field, like for JSON support, this is how they get access to the answer. And let's take a look at it. Here's a quick example showing how you use those numField and field methods in data in the reflect struct field. So you have this type called field that has two fields, the int and the string, and each of the tag, value and value 2. So we create an instance f of type foo, and then we use reflect that type of, you have to type, get the reflect that type for f, and then use a numField method, a simple for loop, to iterate over all of the fields in f. And using the get method, we're then able to pull back the type. We pick up the tag information right here. And so this code, if you run it, it's going to print out A, int, and value on one line, and then B, string, and value 2 on the second line. And there are lots of other methods in reflect.type, but you kind of get the idea. You can access the information that describes the type of the variable by using reflect type of to get a reflect type instance that represents the type of the variable. And the kind of the type determines which methods on the reflect.type instance are actually valid. So in addition to examining the types of your variables, you can use reflection to read a variable's value, set its value, or create a new value from scratch. So to use reflection to interact with the value of a variable, use the value of function in the reflect package to create a reflect.value instance that represents the value of your variable. So just like reflect.type defines lots of methods for finding out information about the type of a variable, reflect.value defines a lot of methods for finding out about information about the value of a variable. We're not going to cover all of them again, there's a lot of them, but let's take a look at how you can use reflect.value to get the value of your variable. Several methods for reading back that value from the reflect value. The interface method returns back your data as an empty interface type. But the type information was under the originally has been lost. You actually have to cast it then back if you want to put it back into a variable. Just like you do with any empty interface that you come across. And while interface works to reflect values of any type, any kind, sorry, there are special case methods that will work for some of the primitive types that are built in. So bool, int, uint, float, string, built-in special case methods in values, you can get those back out directly. This will bytes method that returns back a slice of bytes. So if your value is a slice of bytes, it's built in. Don't know why. And of course, if you use a method that doesn't actually match the kind of your reflect.value, all these things just happen. So you can use reflection to set the value of variables too. However, there are a few things that you do need in order to make this work. So first, you want to be able to use reflection to modify the value of a variable. You have to make sure to pass in the right thing to reflect the value of. And you don't pass the variable in directly. You pass a pointer to the variable indirectly. So in this example, this 8 called var is 5. We pass a pointer to var into reflect value of, so that we can then modify its value. If you don't pass a pointer in, you can still read the value. But if you then try to use any of the methods to write the value, and you try to modify it, you pass in the pointer, then it's going to. That was fun. So since you pass this pointer to reflect value of, you actually have to use lm to set it. So you have to, there's an lm method on value, so there's an lm method on type to get to the actual values being pointed to by the pointer. And so this works for pointers, also works for interfaces. So when you get to the actual underlying value inside of the interface, you also use lm as well. And once you get to the actual method to set the value now, just like there's special case methods for reading primitive types, there's special case methods for writing primitive types. There's a set bool, there's a set int, set float, set string, set uint. And so here in our example, we're going to call set int 2. And if you then print it out of var, you'll get back 2. And for all other types, you have to use a set method. And set takes in a variable of type reflect value, and take in a primitive value. So the value that you're setting does not have to be a pointer, because you're just reading it, you're not writing it. So we're going to use interface to read primitive values. You can use set to write primitive values also. So in our example here, we define other var equal to 2. And other var does not have to be a pointer. We pass into reflect value of, because we're only going to read its value, not write its value. And then we take that var val we got out of it, use set, assign it to another var val, and then print it out, and you get 2. If you have a reflect out type, you can actually get a brand new reflect value without starting from an existing variable. There's a method, there's a function in the reflect package called new, pass it a reflect out type, and it will create for you a new reflect value. It's a pointer to the value of the type that was passed in. So you pass in the int, new pointer val is actually a type pointer to int behind the scenes. Since it's a pointer, you can modify it. Use lm to get the real value, and then call one of the set methods. You can then assign it to a variable using interface, one of the methods for reading a primitive type. So in this code here, we start with x, reflect type of in type, have a pointer to new pointer val to point to x value. We use new pointer val lm set to 20, and we lm int, and we print it back out, we get 20. So we're able to use x, create an instance, create a y off of that value that is defined there. In addition to making instances of built-in and user-defined types, you can also use reflection to make instances that normally require the make function. So there's a make a slicer, a map, or a channel with reflect make slice, reflect make map, reflect make chan functions. In all cases, you supply the reflect type of the value you want to put into the slicer, map, or channel, and you get back a reflect value that you can manipulate with reflection or assign back to a standard variable. And reflection does not just let you make new places to store data. You can actually use reflection to make new functions to reflect make function. So this function expects the reflect out type for the function that we want to make, and a closure with input parameters are type reflect value, and whose output parameters also type slice and reflect value. So here's a quick example. We're going to create a timing wrapper. You're going to pass in any function to, and I'll tell you how long the function ran for. So here we go. There's a make time function. We pass in f, which is an empty interface. So you can pass any function in there. It does not care what the type of the function are. We can put our output parameters. Again, we get the reflect type of, and we check the kind, make sure it actually is a function. And just for simple short code, we're going to panic. But in regular code, for real, it actually return back an error instead. So that way, someone passes something that was not a type function, which you can't confirm at compile time because it's just empty interface. You can catch it at runtime, please. And then we also then get the value of the function, so we can then call that function later. We then call the reflect make function, and we pass in our type, the rf, and we declare this closure. So its input parameters are slice and reflect value. Its output is a slice and reflect value also. And inside of our closure, we call start time now, because current time. We call our function, the reflection of calling the function, get the output parameters, time now to the end, print that on itself, and return back the output from that function inside of our closure. And then in our main function, we turn back an interface representation of our new function that's generated. And let's write a couple of simple functions to test it with. So we have timeme that just sleeps for 1 second. And we have a second function, timeme2, that takes in an int and returns back an int, and it sleeps for that time, and doubles the value, and returns it back out. Just something simple to show it off. And here's some code to actually run it. So we call makeTime function, pass in timeme. It's a pass the value back to a function with empty parameters, assign this variable timed, and then call this function timed. And for time2, we call makeTime function, pass timeme2, and then pass it back to a function that takes in the int and returns an int. And then we call time2 taking into it, and we print it out. And if you run it, you see the output. It says call took 1 second, call took 2 seconds, and the output from our function as well. And if you want to try this out for yourself, I put a link up here. It's on the Go playground, so you can try all these things out for yourself as well. One more thing you can make using reflection in Go, you can make brand new structs at runtime by passing the slice of reflect struct field into the reflect struct of a function. So this is a little bit weird, okay? Because you're making this new type, but you don't have a name for it. So you can't assign it back to a regular variable unless that variable is of type empty interface. So if you want to set or read the values in the struct that's just made up on the spot, you have to use reflection to read it or to write it. So let's see how this works. So we're going to create a struct from scratch that has 2 fields, a string field called name and an int field called age. So first we have to get our types for our fields. We define this variable I int, this variable s string, just so we can get the types out of them. So we'll reflect type of, pass it the int, get something that represents an integer type. Same thing for the string, we pass an s, so we can get something that represents a string type. And then we build a reflect struct field slice out of it. The first one has name, type is the string type. The second entry in that slice is name age, and type integer type. And we then call reflect struct of. We pass it that slice of struct fields. We get back a struct type. And then we take that struct type and pass it to reflect new. We get a struct value. That's a pointer to that struct, so now we can modify its values. And now we can set the fields using reflect values. We can say field set by name, set string Bob, and field by name get age, set its value to 50. And struct val, lm, we call it, that interface turns back a normal variable. This is a type empty interface. You can now print it out, and remember behind the scenes, all the func methods, all the func functions use reflection to actually read the values back out again, so it all works, and you can get the output of name Bob at age 50. And you can try this out again, it's up on the Go playground. Take a look. So you might be wondering, what the heck could you do with a struct that you built using reflection, right? I mean, for the most part, it's not too useful because you can only read and write the fields in the struct using reflection. So I actually did find some things you could do with it. Anyone here heard of memoization? All right, so functional programmers in the audience. Good. So if you have memoization, it's kind of like caching at a function level on a service level. So if you have a function that always returns back the same results for the same inputs and doesn't have any side effects and do anything else like write to a database, you can just remember the results of those inputs, not run that function over and over again. So you can do this in Go. So the secret is to wrap a function in a dynamically generated function that caches those input and output values that have been seen before. And you have a map whose key is the input values, and the value of the map is going to be the output values. And you might think you could use a slice to do this, but you can't. So a slice in Go cannot be a key of a map because it's not comparable. But what is comparable? A struct. So in order to have a struct that actually matches the input parameters for any function that comes along, you can dynamically generate the struct using reflection. So let's see how this works. This one's hardcore. All right, so let's look at our function for making a memoized function. We're taking any function, so input parameter again is empty interface. We'll return back a generated function, which is empty interface also, and an array. We'll try to do a little bit of error handling here in our samples. We use reflect type of to check to get back the type, check the kind, make sure someone actually passed any function. If not, return back nil with errors for functions. Next, we're going to call this function called build-in-struct, which I'll show afterwards in a bit. And that's to be the one that actually makes our dynamically generated struct for us. And if that has errors, we'll return back the error from there. Declare the map. It's going to hold our inputs and outputs, right? Map an interface to a slice of reflect values. And then we have our reflect value of f. This is our function value that we're going to be calling for wrapping. And then we call reflect makeFunc. We pass in our function type. We pass in a closure whose input is a slice of reflect values. and whose output is a slice of reflect value. And inside of our closure, we use our new type, generate an instance of it, and we walk over the arguments that were passed in, and we set all the fields on it to build our structs fields up. And then we turn it into an empty interface right here, and we don't check our map to see if it's already in our map. If the output parameters are already there, we just comma OK, idiom, and go. And if it's not there, we actually call the function and store the values in the map. And then from inside of our closure, return the output values. And then we return back from the actual memoization function, we return back the interface that represents our generated function, and we're done. And so here's that built-in struct function I talked about before as a helper. You pass in the function's reflect type, and you return back the reflect type that represents the struct that we're dynamically generated. And in error, we make sure that it's a function. We know it's a function because we call from inside of our memoization function. If there are no input parameters, that's an error. You have to use one input parameter to make this work. But as long as you do, we build a slice of reflect struct fields. And we iterate over all the input parameters in our function. And we get the type of it. And then we append it onto our struct field we built dynamically out of it. And then once we have our slice of reflect struct field built, we call reflect struct of, and return it back. And there are a couple of things I've left out. If you go to this URL, you can see it on the Go playground. Only limitations there are certain things you can't do in Go. You can't memoize a function that has parameters of type slice, map, channel, function, or a struct that contains those things. Again, they're not comparable, so they can be keys in a map. But the code in the Go playground does actually check for this correctly and report it back as an error. All right, so we can do all these neat tricks with reflection, but how can you use them in your everyday programs? And the answer is don't. Right? So reflection is a tool that's used behind the scenes to make normally impossible things possible. It's hiding in the implementation of some, if not most, of the libraries and tools that you use. We saw the places where Go Standard Library uses reflection, the reasons why it does. So how can you tell if a library is using reflection? The biggest hint is checking the types and parameters. You see, we call a function that has an empty interface as one of the parameters. There's a really good chance that it's going to be using reflection behind the scenes to actually do something valuable with the empty interface. And those are the things that we can do with reflection. Let's talk about what you cannot do with reflection. There's one really big limitation on reflection in Go. And you can use reflection to create new functions. There's no way to create new methods in Go. This means you can't use reflection to dynamically implement an interface at runtime. And so what's the big deal about that? What can we do if we can implement interfaces dynamically? So just like we can generate a wrapper for a function by taking advantage of Go support for generating functions, we can do the same with an interface. So Java actually has Java developers here. All right, so dynamic proxies in Java, used them before? So in Java, you can actually have an interface at runtime implement the interface. And this is really helpful. Combined with annotations, you get this way to move from imperative programming styles to a more declarative one. So you can't do it in Go, but there are ways to work around this limitation. You can generate functions, and structs can have fields of function type. So this isn't an interface, but it looks an awful lot like one. And so I use this idea to create this open source library called Proteus. It's available up on GitHub. With Proteus, you can define the struct type with function fields. You put a struct tag on your field to template with SQL queries. And then you populate those fields by passing an instance of your struct to the Proteus build function, which I have over here. And you pass all the type database to this as well. And this gives you a dynamic type-safe wrapper around SQL queries without using any code generation. So in this example here, we found a struct called DAO. There's a single field, a function called find by name. It takes in this querier and a string and returns a struct of type food. The field is a struct tag on with a SQL query inside of it. And we put the instance of our DAO, we pass it off to build. And now when we get it back, we can actually run our SQL queries by passing reference to the database and the name we want to search for, and spits back a food for you. And so Proteus does all of its magic using reflection. Reads struct tags, generates functions, converts structs to and from the database. If you're doing any SQL work in Go, check out Proteus, see if it works out for you. One more thing to be aware of with reflection, it's slow. So we're going to quick program up to benchmark adding up all the numbers in a 10,000 elements slice. Did it the normal way, did it using reflection, and the reflection version is about 20 times slower. So if you can avoid using reflection, you should do so. If you are going to use reflection, make sure that kind of a cost and performance isn't going to impact what you're working on. All right, so let's take what we've learned so far and go back to one of those use cases that we talked about from the standard library, marshaling and unmarshaling data. So Go provides out of the box the ability to convert back and forth between JSON, XML, and some more uncommon formats like ASN1. There's this binary number format, and there's this home-run serialization format called GOB, making pure Go remote procedure calls. Don't use it ever. They don't know what they're thinking. But there's one interesting oversight in the Go standard library. So there's no out-of-the-box way to marshal and unmarshal a CSV file. You know, you can read a CSV file into a slice of strings. You can write a slice of strings back out to a CSV file. But there's nothing that will map those strings to structs. So as a final exercise to pull everything together, I wanted to go through the steps to build a simple CSV marshaling library. So as I said, Go has a CSV new reader function, new writer functions to read and write CSV files, but there's no way to map the data on those fields to your struct. So it'd be nice to be able to define a struct. You can put struct tags on it. This can be for JSON or XML. And be able to take the output of the CSV new reader function and turn it into a slice of our data type. And it would be nice to go in the other direction as well, right? We take a slice of structs, turn it into a slice of strings, put it into a CSV file using CSV writer. And with all the things we've learned about reflection, we can build this. It's actually not that hard. This one's actually a lot easier than the other ones. So let's start with loading data from a CSV file into a Go struct. So you want to write the code to a single row from a CSV file, and then write a second function that reads all the rows in a CSV file. So the CSV libraries in Go gives a slice of strings to represent a row in a CSV file. So let's write our unmarshal function to assume that we have a slice of strings and want to copy into an instance that's been passed in. So we pass in the header, so we can map the columns in the CSV to the fields in our struct. If anything goes wrong, we return back an error. First thing we need to do is make sure the right kind of variable is passed in. It has to be a pointer to a struct because we'll be modifying the values inside of it. So we use reflect value of to get the value, use kind's available on value as well as on type. And check to make sure it's actually the pointer, and also make sure that what it's pointing to is also a struct as well. And if that's all, either of those things are true, you have to return an error out. Next, we're going to build up a map that will translate the column names in our CSV tags into positions in the data slice. So just walking over the header slice and building a map with the keys, the column name, and the values of the column position. And then we're going to loop over every field in the struct that was passed in, and we're using reflect.type to get the value of the CSV struct tag on each field. If the field doesn't have a CSV struct tag, just skip over it. If it does have it, use the position information from that name pos map to find the corresponding column in the data. And we get the kind of the value of the field, and depending on the kind of the data, if we convert the data into the column to the right format and set the value of the fields. For in fields, use string convert.parse and you do a field setting. And for unsigned ins, use string convert.parse uint and do a field set uint. And for Boolean, string convert.parse bool and use field set bool. And for strings, just do a set string. It's really straightforward. Other types, simple example, just going to return back an error. And that's it. That's all you have to do to convert a single row in a CSV in Go to a struct using reflection. Not that much more work to actually process an entire CSV file into a slice of Go struct. So let's see what's involved. So you have our unmarshal all function. Takes in two parameters, a slice of string. It contains all of the data in the CSV, and an empty interface parameter that holds a pointer to a slice of structs that we want to populate. The slice should be empty because we use reflection to just append elements onto it. And you have to make sure the variable passed in as our v parameter is in fact a pointer to a slice of structs. So first you get the kind, make sure it's a reflect pointer, get the element for that, make sure it's a slice, and then get the element for that and make sure it's actually a struct as well. And the rest of the code, pretty straightforward. So you assume that first row is a header, and then we're just going to loop over all the remaining rows. Use reflect new to make a new value for the type of the struct. Call the unmarshal function that we just wrote, and if there's no errors, we use the reflection version of append to what's called reflect append to add the element to our slice. And that's the whole function. So walk through the steps to turn a CSV into a slice of structs. Let's go the other direction. Let's write out a slice of structs into a slice of strings using reflection. And just like before, we'll start by getting it to work for a single row, and then we'll convert a single struct into a slice of strings, and then we'll build a solution that works for an entire slice of structs. For the marshal function, we have one input parameter that needs to be a struct of any type. So we have to use empty interface. Remember, we're reading it this time, not writing it, so you don't have to pass any pointer to it instead. And the function returns back a slice of strings and an error. And so again, reflect value of, check the kind immediately, make sure that was passed in is actually the correct type, correct kind. The rest of the code, not too much to do. You do reflect type of variable is passed in. For each field, iterate over the fields, see if that field has a struct tag on it, CSV. If it doesn't, then skip it. If it does have a field with a CSV tag on it, we do a switch depending on the kind. And here's the cases if the kind of the field is integer unsigned. Just string convert format the int and append it onto our output slice of strings. That's int and new int. Here it is for string and for bool. For strings, take the string and the value, append it onto our row. And for the boolean, string convert format bool, append it onto the row. And again, all of the kind just produce an error because it's a simple example. And after we loop through all of the fields, we're done. So that's all we need to do to marshal a single struct into a slice of strings. To turn a slice of structs into the output we need for a CSV file, we also need to build a header. And so let's write a quick helper function to build a header. Just like Marshal, we have our Marshal header function. Takes in the slice, has an empty interface, returns back a slice of strings and an error. And that slice of strings will contain the header column names. Again, reflect type of v. And check to make sure that was passed in was in fact actually a struct. Again, not modifying it, so you pass in a struct directly, not a pointer to a struct. And now just walk through all of the fields inside of our struct. And we check to see if they have a CSV tag on them. If they do, we append the value of that CSV tag onto our slice of strings. And then return it back. And that's all you need to do to build up the header for your CSV. All that's left is building the Marshal all function. Takes in a single parameter, expect to be a slice of structs, but in order to support a slice of any type, again, empty interface, returning back a slice of strings and an error. So we again reflect value of, get the slice value, make sure to reflect that slice, and then check the element, make sure that it's a slice of structs. And then we have our output variable declaring, so the slice of string. Set the first row for the output to Marshal header's output. Pretty straightforward, so append it on after you call Marshal header. And then we iterate over all the things that are passed in. So there's a len method that's available via reflection. You get the length of the slice. You pass each entry in the slice off to Marshal using an index in that slice. Again, these are reflection methods that are available. And then you append the output back on to our output slice. And that's all done. You print out your return back out your slice of strings, and you're done. So let's go back to those original slides where we first described the CSV problem. These are data in a variable called data, where the first row is a header. Next three rows have some data in them. Use CSV new reader that's supplied from the standard library. Use a string new reader to read the data out of the variable, and then put a slice of strings to the variable all data. We then find a slice of my data, call our loop and Marshal all function, and then print out the results. So then you pass any pointer to your variable type slice of my data. And you're printed out, you get the following output. Data is now loaded into structs. And go back in the other direction, right? So we'll call our Marshal all function, pass the entry that is populated. Doesn't have to be a pointer this time, because we're not only reading it, not writing it. Get back a slice of strings, strings builder, write it out to CSV, and then we print it back out again. And you print it back out, you get back your CSV. And so, reflection solved this problem really nicely, and it all integrates back in with the standard library in Go. So it's nothing really special, it fits right in. And that's it. Went through a lot of code. If you want to look at it in more detail, use it in your own projects. Up on the Go playground, URLs up on your screen. So walking through the creation of our CSV Marshaling and Unmarshaling library should give you a taste of the kinds of problems that can be solved with reflection in Go. It's not a solution to reach for all the time, but when you have a problem that seems impossible, there's no commonality in the data, or because the data is dynamic, reflection is your secret weapon. So thanks for your time. Do you have any questions? Yes.
Yeah, so is there any good story behind why the type of a pointer is empty string?
I wish I knew. It makes no sense to me. I don't know of any story for it. Or like a slice also. Why would it not have a type? I don't have a name. It obviously has a name. It has a kind, but
I don't know. So you have to reference the base type of your LM. If you look at the Go types package, like all the LM stuff are based off of what those structs in the Go types package.
Anyone else? That's where you're stuck? I don't know. Yeah.
So, given all the scenarios of what works and what doesn't work, is there any good package that would sort of like smart reflect, that
Yeah.
manages, or it seems like it's pretty straightforward once you know all the intricacies, but it sounds very cumbersome. So, is there some
I think someone did write a smart reflect package to try to clean it up and get a better API. So the Go team is very hostile to making reflection any better. They don't want people to build programs and depend on it. They want to remain something with really sharp points on it, so that people don't start writing programs that are 20 times slower than they have to be, because then people go back to Go and say, oh, it was a terrible language to do this. So I think there's a package on GitHub for smart reflectors that would actually do that, but it's not ever for making this a library. Other questions?
Okay, I'll shoot.
All right.
Simple one. How does the use of reflection impact the way you work about test coverage?
Oh, that's actually really good. So you do have to be careful, right? Because I can talk on code coverage too. So if you're traditionally have like 100% code coverage in your code, so if you want all the lines to turn green, that doesn't mean you actually test all the possibilities in your code, right? There's lots of ways just like to exercise the line and miss some of the things that happen. So especially when you work with these things that are type empty interface, you have to try out different values and pass in to make sure you actually are hitting everything. Otherwise, you're going to look like you have complete coverage, and then someone's going to make a mistake and pass the wrong thing in, and it's going to blow up. So always be careful. If you don't put those kind checks to make sure that you actually are working with the right kind of data underneath it, so that the methods work correctly. If you leave those off, you're going to blow up. And if you don't write tests that exercise those things that you've covered all the possibilities, you're going to have surprises eventually.
It sounds like that's another use case.
Yeah, there's a GoFuzz package. I don't know if they're using reflection on it or not. I've looked at GoFuzz too closely, but it probably is something like it to actually take it apart and see what the dollar values are. But yeah. If anyone hasn't tried fuzzing, anyone here familiar with fuzzing? All right, cool. Other questions?
I've used reflections like a map package before.
Mm-hmm.
So like you know like the standard types, like size of things, without using reflection, but people could have like aliases and those weren't good on. So it falls back to reflection at the end when it's tried and all the like standard
Yeah, Go and math seems funny pairing because they included complex numbers as a base type, but it's really kind of not a great language to do mathematical operations in. Because arrays are fixed size, so you have to do things about slices, so you can look at fast matrix lookups. And it depends on how your speed envelope looks like. If the performance is okay, it's fine, but if you have to worry about just as fast as humanly possible, then Go's math stuff sometimes falls behind on C libraries.
I'm just curious if you looked at reflect light.
Is that the one is that the smart library?
No.
Oh,
That's part of this
This is the
internal
library. Oh, yes.
internal package for the errors.
I
handling as it is.
I actually reported a bug in it last week on GitHub.
Tell us.
Yeah, there's a Go philosophy that a little copying is better than a little dependency, and it kind of bit them because there's a reflect light package that's used internally inside of Go for doing some things, like the errors as and error support. Rather than having the errors package depend on reflect, there's this other internal package called reflect light that has a lot of the reflection functionality copied out, enough to support these internal packages.
Sounds like they're avoiding a cycle rather than.
They could be. There's been a couple places where they have copies of code. They could have broken it out, so reflect like alias things back out of reflect light, but they don't. And because it's alias back out, they changed the definition of a map in 113 and forgot to copy that new definition over to the reflect light package. So if you have an error that's built on top of a map, and you called and it was in the chain of the wrap chain, and you called errors.as, it would pass the recorder. If the method name was long enough on something, it was weird. The trigger, I just happened to run across it. Some triggers working on here, and they fixed it like in 3 hours of getting process. So yeah, reflect again. Everyone messes this stuff up. Reflection is going to be very careful. Other questions?
mentioned it's 20 times slower than Golang was. Is integrated with other languages that Python would be.
I have not. So that's fraud. This comparison. Right? There's a whole benchmarking website which has all that stuff up there. Go in general is much faster than Python usually is, and part of it is a number, especially doing mathematical operations like Python. All the NumPy stuff's not a secret. You can run fast enough, and Ruby is slow. Hold on, something Ruby developers here. Ruby is really slow. Yeah, so I don't know if it goes 4 times faster than Python, so maybe it'll get back to parity. I wouldn't do it just for parity's sake. And Python doesn't really have much. Does Python for function have much to do this, or I haven't written Python that does that kind of as well.
You can access a lot of that information directly, like attached to classes and things.
Yeah.
I'm sure there's a dedicated reflection package, but a lot of it's just attached directly to the
Right. But Python is like infinite size, right? It's like it'll just grow as you know. So it's actually not like math like in 64. So if you want to do math on like on small types in Python, it's very slow because I'm really using it. So it's just all my information. So other questions? Yes.
So I've got a project where I wanted to call a function to reflect, and I benchmarked it, and it's actually that calling a function seemed to be 100 times slower. So I thought, well, that's too bad because I really wanted to use that, and so I started looking into how could I like fork the reflect package to try to make changes to it. Well, it seems like if you want to do that to a standard library package, you really have to fork the entire all of Go. So I did that, and it's actually not that hard. So I did that, and I found an issue in GitHub where they had some suggestions for how to make it faster because they recognized that it's slow to call a function. And so I started working on that, and I managed to make it quite a bit faster, but I'm not sure that the changes that I made would be acceptable by pretty much anyone because I just ripped out a bunch of the checks that they do. But I'm curious to continue working on this, but I would like to bounce ideas off to somebody else has an interest in seeing.
That's really clever. That'd be interesting. Yeah, like I said, they're not too concerned about like trying to speed things up usually. Have you talked to anyone on the team about like contributing it back, or?
I have not because I'm nowhere close to having code that I think they would accept.
Okay.
But just the presence of the issue is like from 2014, so it's pretty old, and I don't know if they would still be interested. But they have a lot of, they do use that functionality in other places in the standard library. And so I think if you come up with an improvement for it, they may be interested. The improvements that I came up with are mostly if you plan to call it repeatedly. So you cache some things before you call it, and then you use those repeatedly. And you can, if you call it 2 or 3 times, you're way faster. If you call it 1,000 times, you're way faster.
That's good. Yeah, a lot of the use of reflection in the standard library are around I/O. So since I/O costs so massively predominate when you're doing any kind of calculation of how much time it is, that if you sped it up from 100 times, a function call from 100 times faster to 5 times faster, then if your database call over the network is still, at milliseconds on and nanoseconds, don't make that much of a difference. That's the other thing to worry about when you're doing reflection, talking about being slow. It's slow compared to code running. One network call kills a lot of performance optimizations. So, any questions?
Are generics still coming in version 2? If so, are they based on reflection or are they done something else? Or do you know?
I do know a little bit about it. They talked about it at GopherCon this year. There was a contract. So last year at GopherCon, there was a presentation where they talked about this contract API. They were talking about doing generics in Go. It was pretty universally hated. You could write a code snippet to describe what was legal, and so it was like unclear that this little code snippet would actually work or not. And so this year they released something that was a lot more like the current interface. And so you basically say which methods are available on this contract that you've declared. And it's, I don't know under the covers, they've been very vague of how implementation is going to happen.
It's not compile time, so it's not based on reflection.
Well, they've said that there may be compile time and maybe runtime. They won't say which they're going to do because they don't want to make them compile time too much and they want to slow it down at runtime. So their answer has been, have they released any sample code yet? Is there information? Yeah, I haven't seen it yet, but I know they were saying the spec doesn't say whether it happens at runtime or compile time. The compile time still checks to make sure it's valid code. It just won't it may delay till runtime the first time it actually generates the function that you're going to be calling. If you have different size data types being passed around, different sizes on the stack, you pass back and forth, so you have to be careful with that. So probably, the product using reflection, but it is probably coming. So, the homework set of thoughts.
No, I just wonder if that would result in improvements in reflection performance, if it was based on reflection.
I don't know.
It would remove a lot of the use cases for
It-
reflection.
Yeah, that's absolutely true.
You could write them, people use reflection to write generic code.
I would assume the goal would be to make it faster than reflection.
Yeah, agreed.
Faster reflection, time safety.
Yes.
Type safe code.
Any other questions?